482 kilometers from the calm and misty coast of Oregon, in the abyssal depths of the Pacific, resides a colossal geological force whose recent and dramatic awakening has set off alarms in the international scientific community. This colossus is the Axial Seamount, recognized worldwide as one of the most active and therefore most intensely monitored underwater volcanoes on the planet. Mount Axial is no ordinary peak. It rises majestically more than 1,100 meters from the inhospitable seabed, and its summit, which houses a vast caldera, is located just 1,400 meters below the surface. Now this giant is emitting unequivocal and accelerating signals that point to a single dramatic event. A new eruption is imminent. Leave a like, subscribe, and share. Let's begin. For decades, Mount Axial has functioned as an unparalleled natural laboratory. Its position is geologically privileged. It sits directly on the axis of the Juan de Fuca Ridge, an active boundary where oceanic tectonic plates are slowly separating. This dynamic makes it a focal point of intense hydrothermal and magmatic activity. Scientists are not only studying it for its crucial importance in understanding plate tectonics, they are also investigating it for the unique, exotic, and extreme ecosystem that has managed to thrive around its boiling hydrothermal vents. However, in recent months, the situation has changed drastically. The data collected by a sophisticated and permanent network of sensors, and more crucially, the recent information obtained by an advanced unmanned underwater vehicle, drone state-of-the-art scientists, have transformed mere routine readings into an eruption forecast with an alarming and high degree of certainty. The monitoring effort on the Axial Seamount is a feat of engineering and volcanology. It is led by an elite collaborative team including Professor and researcher Bill Chadwick of Oregon State University, along with his colleagues from the University of Washington and the University of North Carolina at Wilmington. This consortium relies on a network of state-of-the-art instruments permanently installed on the ocean floor. This infrastructure is an integral part of the Oregon Coast Ocean Floor Observatory, which in turn is a vital component of the ambitious Program Ocean Observatories initiative funded by the U.S. National Science Foundation. The key to predicting the eruption of Axial does not lie in the direct observation of visible phenomena such as the smoke or lava that characterize terrestrial volcanoes. Instead, it is based on the detection and analysis of two subtle but extraordinarily powerful indicators that act as the seismograph of the volcano's heart: seismicity and ground deformation. The ascent of magma from the depths of the Earth's mantle exerts monumental pressure on the volcano's magma chamber. As this internal pressure intensifies, the magma relentlessly seeks an escape route, forcing its way through cracks, fissures, and planes of weakness in the surrounding rock. This violent process of fracturing and displacement of rock generates thousands of small earthquakes, known as microseisms. Background seismometers, strategically located around and within the volcano's caldera, have recorded a dramatic and sustained increase in both the frequency and intensity of these tremors, a clear sign that the rock is breaking apart. Seismic activity is the pulse, the vital signature of the volcano, Chadwick emphasizes. In the weeks and even months preceding the previous historical eruptions of the Axial, documented in 1998, 2011, and 2015, we always observed this unequivocal pattern, a progressive and exponential increase in tremors as the magma literally broke through the rock. The seismic pattern we are currently recording is strikingly similar, almost a carbon copy, to the one observed just before the 2015 eruption. This suggests to us with a high degree of confidence that we are in the final and critical phase of magmatic pressure buildup. The second crucial and complementary indicator is the swelling or deformation of the volcanic massif, a phenomenon known technically as inflation. As the magma chamber fills with more molten rock under high pressure, the seafloor at the top and flanks of the volcano rises. To measure this millimeter-level movement, scientists use an ultra-precision technology, bottom pressure gauges, BPR. These highly sensitive instruments are capable of detecting minute changes in water pressure just above the seabed. These changes are directly correlated with the uplift, swelling, or subsidence, deflation, of the seabed. Following the 2015 eruption, the Axial Seamount experienced an abrupt subsidence, a rapid deflation phenomenon that occurred as the released magma partially emptied the chamber. Since that event, the volcano has been inflating, regaining the lost elevation at a steady rate. However, recent data has shown a remarkable and unexpected acceleration in this swelling rate. Chadwick and his team's central prediction is based on a proven model. The volcano swells until it reaches a point of critical stress or fracture threshold, at which point the roof of the chamber gives way and the eruption occurs, releasing the accumulated pressure. The most worrying thing is that the volcano has already reached and even surpassed the maximum swelling levels that were observed immediately before the previous eruptions. The rock is at the limit of its elasticity. While the network of fixed sensors provides a continuous and invaluable database, it was the incursion of unmanned underwater vehicles, often referred to as drones, scientific ROVs or AUVs, which allowed for a visual perspective and mapping of terrain deformation with unprecedented accuracy and detail. He drone a robust and autonomous scientific platform equipped with ultra-high-resolution sonar and specialized cameras capable of operating in the absolute darkness of the deep ocean was deployed to carry out a thorough and detailed survey of the axial caldera. The objective was twofold and urgent. On the one hand, to recover the data records stored in the bottom instruments that do not transmit in real time. On the other, and more importantly, to obtain detailed images of any evident physical changes on the seabed, such as the formation of new cracks, fissures, or the appearance of new hydrothermal vent fields. Leave a like, subscribe, and share. What the drone. The recording and transmission to the surface was, in the admission of one of the lead researchers, absolutely shocking and served as visual, irrefutable, and urgent validation of the seriousness of their predictions. The state-of-the-art multi-beam sonar on board the drone scanned the seabed, creating a very high-resolution 3D topographic map of the caldera. This mapping revealed the presence of new and extensive fissures that had not been previously documented. These cracks were concentrated especially along the flanks of the boiler and in the main ventilation area. These fissures are the direct and visible physical manifestation of the violent swelling of the volcano. They represent the potential pathways and conduits, already open, through which the rising magma will eventually make its way to the seabed. The dimensions of the cracks turned out to be longer, wider, and significantly more numerous than scientists had anticipated at this stage. This finding confirmed that the surrounding rock is stretching and fracturing to its structural limit. Thermal imaging cameras specialized in detecting temperature variations recorded another crucial and very worrying phenomenon. Instead of finding only the usual localized hot hydrothermal plumes, the vehicle passed through vast areas where the basal temperature of the bottom water had increased in a generalized and diffuse manner. The most revealing thing was the presence of an anomalous thermal haze. Large areas of the seabed, previously thought to be inactive or cold, were now emitting a weak but constant flow of warm water. This phenomenon is interpreted as the massive percolation of hot fluids through the porous rock, heat that can only come from magma that is already dangerously close to the surface. This thermal mist is considered a direct and immediate precursor to the eruptive phase, as it indicates that seawater is interacting on a large scale with magmatic heat through microscopic fractures. Perhaps the most moving and visually striking recording for the non-scientific public was the one that drone obtained information on the immediate impact on the unique ecosystems of hydrothermal vents. These ecosystems, which defy all biological logic by being based on chemosynthesis and not sunlight, are home to giant tube worms, clams, shrimp, and crabs adapted to survive in extreme temperatures and fluids saturated with toxic chemicals. It captured heartbreaking images of marine life colonies experiencing catastrophic heat stress. In several critical areas, tube worm colonies were visibly pale, shrunken, or completely collapsed. Large quantities of dead or dying clams and mussels were observed scattered across the seabed. The widespread increase in temperature and the violent alteration of the chemistry of the hydrothermal fluid, both caused by the proximity and heat of the rising magma, were selectively exterminating the species less resistant to heat. This biological evidence, captured in high definition, provided a visually and emotionally powerful confirmation that the geological process was at its terminal climax. The consolidated information compiled by the drone has solidified the team's predictions. Chadwick and his colleagues predict, with a high degree of scientific certainty, that the Axial Seamount will erupt sometime between now and the end of the year, making it necessary to maintain the highest level of vigilance. Fortunately, the eruption of the Axial Seamount is, in the vast majority of modeled scenarios, an event confined to the ocean depths. Given its location almost 500 kilometers off the coast of Oregon, it is extremely unlikely that this event will pose a direct tsunami risk to coastal populations. The lava that is ejected will be cooled almost instantly by seawater at a depth of 1,400 meters, solidifying into the characteristic pillow basalt formations. However, the imminent eruption carries significant scientific, operational, and risk management consequences. Risk of equipment destruction. The expulsion of hot lava represents a direct risk of annihilation for the bottom-mounted sensors that have provided crucial data for prediction. The event will be a litmus test for the robustness and resilience of the program's high-tech infrastructure. Ocean Observatories Initiative. Invaluable scientific opportunity. An active and predicted eruption is a golden scientific opportunity to study, in real time, fundamental geological processes, the formation of new oceanic crust, the carbon cycle in the depths, and above all, the immediate response and resilience of chemosynthetic ecosystems to a cataclysmic event. Navigational and oceanographic surveillance. Although the risk of tsunamis is minimal, continuous monitoring is imperative. In addition, the hydrothermal plumes and particles released during the eruption can be detected by satellites and research vessels, providing crucial data for global oceanographic modeling. Chadwick's team is now on high alert, preparing for the rapid response phase to the eruption. This implies having underwater vehicles and oceanographic vessels ready to be deployed immediately once the seismometers confirm that the eruptive phase has begun. The goal is ambitious: to reach the site while the lava is still actively flowing in order to sample volcanic gases, obtain samples of the newly formed lava, and visually document the initial stage of the event. Axial Seamount is not merely a volcano. It is a powerful and dramatic reminder of the immense and often hidden energy that pulsates beneath the surface of our planet. He droned by, descending into absolute darkness and bringing to light the growing cracks, the anomalous heat, and the imminent death of life on the seabed. It has provided the final and definitive proof: the giant has awakened. The Pacific and the global scientific community are preparing to witness a new and violent chapter in the history of the Juan de Fuca Ridge. Like, subscribe, and share. Until next time.